Hello everyone and welcome to chapter number 3 in the three-phase induction machine course. In this chapter we're going to cover power and torque speed characteristics. As a quick reminder, or for those who didn't watch the previous videos, in chapter number 0 we covered the revision session and concepts. Chapter number 1 we covered the rotating field theory, and chapter number 2 we explained the construction, machine construction in details, theory of operation and equivalent circuit. What are the contents of this chapter? In this chapter, we're going to cover the power flow diagram and efficiency, and then we're going to look for the torque speed characteristics, and then we are going to wrap up this chapter by a group of examples. So once we finish this chapter, we will know the mechanical performance. In chapter number 2, we covered the electrical performance. We calculated the current everywhere in the motor, but here we are going to know the power everywhere in the motor, what's the torque, what is the speed of the motor, and then we can calculate the motor efficiency. Also, we are going to delve more in the torque speed characteristics to know the key points in these characteristics. So let's start this video number 1, by explaining the power flow diagram. To explain the power flow diagram, we need to have a refreshment about motor equivalent circuit. We have here stator side, which includes core resistance and stator resistance, and the rotor side we have the rotor resistance. The rotor resistance can be divided into two parts. One of them is the physical rotor resistance, and another one can represent the mechanical power, which is R rotor 1 minus S over S. So let me remind you that power is active power, is calculated in watt. So all the reactance will not contribute to this calculation. So we are searching only for the resistive elements, or any voltage and current, and cosine the angle between them. So now we can look for the motor construction and see how the power flows from the input up to the shaft. So how the power flows in the induction motor? We have here stator, air gap, rotor, and the shaft. So the power will be input from the stator side, and we have the power output in the shaft. So let's look here how the power flows from the input to the output. We have input power, three-phase power. And we have in the stator loss, because we have stator resistance, and we have core loss or iron loss. And this core loss or iron loss can be combined with the shaft loss, mechanical loss. Sometimes we can put it here, sometimes we can put it there. And then the difference between input power and stator loss will be the power we're going to transfer the air gap or cross the air gap going to the rotor side. This air gap power will be divided to some losses, and then we are going to have a useful power. So this air gap power we are going to take from this value, rotor copper loss, and then we are going to have what we call it mechanical power inside the motor. To have the mechanical power in the shaft, we are going to take out from that one the rotational loss, and then we have what we call it the shaft power. So what you see in the left side here is all the losses, and what's in green is the useful value. So we have here input power, which includes useful power and loss. So we are going to have here what we call it the losses. So that one in the stator, so we have air gap power. From this air gap power, we have rotor copper loss, and we have developed power. And from this developed power, we can subtract the rotational loss, and we are going to have the shaft power or useful power, net power or brake horsepower. So now we are going to construct the power flow diagram using the approximate equivalent circuit. Why you are using the approximate equivalent circuit, not using the exact equivalent circuit? You can use it, no problem. But I'm using the approximate equivalent circuit because usually we use that one in the analytical solutions. So we are going to build the power flow diagram. As we can see here, we have input power, we have air gap power, developed power, and output power. Efficiency is definitely output power over input power. We have certain losses here. We have the stator loss, like core loss and stator copper loss. We have rotor copper loss, and we have rotational and mechanical loss. If rotational and mechanical loss is neglected, developed power will be output power, and efficiency in this case will be developed power over input power. Sometimes core loss will be combined with rotational loss. It depends on the manufacturer. So output power, they can call it useful, net, shaft, or brake horsepower. It depends on the textbook. It depends on the industry manufacturer. So we are going to use any of these words. So this is the power in the shaft: useful power, net power, output power. So let's start by input power. We're going to start from the left side, from input power. We know that one is a three-phase circuit. This equivalent circuit is per phase. So the input power, as we had in chapter number 0 revision session, will be something like 3V phase, I phase, cosine phi. Respective then the machine is a star or delta, so you are going to search for phase voltage, phase current, and the angle between them, where phi is theta V minus theta I, and cosine phi is the power factor. Also, you can use the equation root 3 V line I line cosine phi. Let me remind you again that cosine phi is the angle, or phi is the angle between V phase and I phase. So when we are going to look for this circuit, first resistance we are going to see here is the core resistance. So that one will be 3I core square R core. And then we are going to find the stator resistance, where the current going through this resistance is a rotor current now, because we use the approximate equivalent circuit. But if you use the exact one, so that one will be I stator square R stator. But that one is multiplied by 3 because we have three-phase circuit. So that one 3 I rotor square R stator. So these ones are losses, as we can see here. And the difference between input power and stator loss will be the air gap power. So we can write that one. Air gap power plus stator loss give you input power. So this direction will be addition. This direction will be subtraction. So input power minus stator loss should give you the air gap power, as we can see here. So power input minus stator loss give you the air gap power. The power going to the rotor cross the air gap. So I need you to notice here that R rotor plus R rotor 1 minus S over S should give you R rotor over S. So the total resistance in the rotor side is R rotor over S. So that one is a three-phase power, so we can write it in this equation, 3I rotor square R rotor over S. But we divided R rotor over S to two components. One of them is physical resistance R rotor, so that one can give you a rotor copper loss. And R rotor 1 minus S over S, that one is a fictitious resistance, can represent the power converted from electrical to mechanical inside the machine. So we can calculate the developed power as 3I rotor square R rotor 1 minus S over S. And definitely we can write the rotor copper loss as 3I rotor square R rotor. Can you notice here that B gap equal 3I rotor square R rotor over S? And B copper loss is 3I rotor square R rotor. So the relation between them is S. And also here B developed 3I rotor square R rotor over S multiplied by 1 minus S. So the relation between them is 1 minus S. So we can write this equation as rotor copper loss equals S B gap. And also B developed is B gap 1 minus S. So we can use here this triangle. So look for this triangle. B developed plus rotor copper loss should give you air gap power because we have addition in this direction. So if you're going in this direction, you're going to add. If you're going in this direction, you're going to subtract. So B gap minus rotor copper loss give you developed power. B gap minus B developed gives you rotor copper loss. So we have a relation between these three together. So if we're going to the left side, we're going to add. To the right side, we're going to subtract. If we're going to the shaft, we have rotational and mechanical loss. So P developed minus rotational and mechanical loss give you the output power, and definitely you are going to have efficiency, as we mentioned, P power output over power input. Before we end this video, let us look to the relation between air gap power, developed power, and rotor copper loss. As we mentioned in the power flow diagram, the relation between them is 3I rotor square R rotor over S to 3I rotor square R rotor to 3I rotor square R rotor 1 minus S over S. So if we cancel the common factors between them, we find the relation is 1 over S to 1 minus S over S. So if we multiply by S, so the relation between them is 1 to S to 1 minus S. So now we have a power triangle, B gap, B developed, and we have rotor copper loss. The relation between them is 1 to S to 1 minus S. What will I watch in the next video? We are going to cover the torque speed characteristics. Once we finish that one, we are going to finish the mechanical performance. Then we are going to solve examples about electrical performance and mechanical performance. See you in the next video.